So we're going to raise this power input to 5,000. Let's say 5,500. On the worksheet, as you can see, we have created, we have raised, initially using 10 kilowatts, we were completely having a vapor fraction of 0 and 0. But now we are having gases, predominantly gas here, about 84% of gas in the hydrogen outlet, and for the oxygen outlet, it's predominantly water. There's about 13%, 14% gas approximately. Now to look at them with respect to composition, for the hydrogen outlets, we're having hydrogen gas of 83%, 84%, potassium hydroxide of about 16%, and insignificant water 0.2%. For the oxygen side, we're having predominantly water, still 81%, water 0.5% rather, 5% of potassium hydroxide, no hydrogen because it's oxygen. No hydrogen goes to the anode side, just oxygen going there, and water. The hydrogen goes to the cathode. So for the oxygen, we're having approximately 14%. This is only the percentage. No, it doesn't represent the quantity. The usual way to find the quantity is to multiply the fractions by the flow rates, and we're looking at the mole fraction, so the mole flow rate. So you multiply that to get the quantity. That's hydrogen produced. For the hydrogen produced, we currently have a molar flow rate in the hydrogen. The molar flow rate is 82.86. 82.86 multiplied by the mole fraction of hydrogen, which is 0.8360. When you do that, you have 61.27 kilograms of hydrogen. And for the oxygen, let's do the same thing for the oxygen. We have 256.1 kilogram mole per hour multiplied by mole fraction for oxygen, which is 13%. When we do 0.1353 times 256.1, we have 34.65 of oxygen. This is the quantity that we have for the oxygen. But now we do not have the value to compare it with to know if we have to be able to calculate our recovery rates, the product yields basically. To do that, we have to look at the inlets. Looking at the flow rates, it's 304.3 molar flow rate. Now for the composition, this is where the problem comes. Hydrogen and oxygen at this point have not been produced yet because it's still in water, so it's a mixture right now. We do know that there is hydrogen component inside and hydrogen and oxygen inside water, but they are in the form of mixture, which gives water. They are not in their distinct components, so we do not have a mole fraction value assigned to them. As such, we do have to go back a little bit to our elementary chemistry to determine the mole fraction inside the mixture. So we have to draw back to our elementary chemistry, which sucks. Well, we have no option. From our elementary chemistry, we understand that to get the number of moles of a substance, we divide the mass of the substance by the molar mass of the substance. In this case, our substance is H2O that we're considering. We already have the mass of H2O, which is 5,000 kilogram per hour, which is our mass flow rates, also mass. And for the molar mass, we have to calculate that, and the molar mass is simply the molar mass of hydrogen plus the molar mass of oxygen. Now for our hydrogen, in this scenario, it's H2, which means the atomic number of hydrogen times the 2 moles that we have for the hydrogen. An atomic number of hydrogen is 1, multiplied by 2 gives us 2. And for the oxygen is also, the oxygen in water is just 1. We have 1 mole of oxygen, and the atomic number of oxygen is 16. So 1 times 16 gives us 16. And 16 plus 2 gives us 18. And that is our molar mass for water combined. For water, combining the molar mass of hydrogen and the molar mass of oxygen. That's 18. So the number of moles of water is 5,000 divided by 18, which gives us 277.7 kilomole per hour. Now that's the number of moles. So going further deep to get the number of moles present for our hydrogen and oxygen, we consider our electrolysis reaction, which is 2H2O, which is as a result of 2H2 plus O2. Now the water electrolysis breaks down water into hydrogen gas and oxygen gas, which we already know. But to balance the equation, it's slightly different from our regular H2O. We have to add a 2 to the H2O to balance the equation on both sides. With that, we have 4 moles of hydrogen in total, and we have 4 moles of hydrogen and also 2 moles of water, 2 moles of oxygen rather, which when we break it down to electrolysis, we have 4 moles of hydrogen also and 2 moles of oxygen. And as you can see, that the reaction is balanced. And if you take notes, you could see that the amount, the mole ratio is 2 to 1 for our hydrogen to oxygen. So for every 2 moles and 1 mole, for every 2 moles of hydrogen gas and 1 mole of oxygen gas, we get water. We get 4 moles, well, 2 moles of water actually, delivered like that to balance the equation. So indirectly, what it says is that the number of moles present in water is the same as the number of moles for our hydrogen. And as for the oxygen, since its mole fraction ratio is 2 to 1, that means that's half of that. The number of moles for the oxygen is half of the number of moles for the hydrogen gas. So all we have to do is, since we have agreed that the number of moles for oxygen is also 277.7, so and for every 2 moles of hydrogen gas, we have 1 mole of oxygen gas. So all we have to do is just divide 277.7 divided by 2, and that gives us about, divided by 2 gives us 138.88 mole per hour. So that's the amount, the total amount of hydrogen gas we have inside water and oxygen we have. Basically, that's the amount going inside the electrolyzer, inside the water mixture. And what we're able to extract, to produce rather, after electrolysis in the outlets of our electrolyzer was just 69.27 kilomole per hour for our hydrogen. So you can see out of 277, we weren't even able to get one fourth of it, quarter of it probably. So, well, yeah, we weren't able to get quarter of it. So we still have a long way to go with respect to our electrolysis. And for the oxygen, we were not able to get even half of it. Yes, even half of it, because we only have 34.65 kilomole per hour. So we still have to work on that process. So let's see if we could increase our power. For those of you who do not understand what I did, I think you might have to consult other better chemistry sources, because chemistry has never been my stronghold. I just tried to explain it best as I could. So for our power, we have to go back inside our electrolyzer and increase the power. So see the parameters. So let's say we increase this to 6,000 kilowatts, and you can notice that we have an error, basically trying to tell us that the power input is too much for our process. That's my guess. It exceeds the handling capability for what we imputed. So it's a function. It's probably related to the flow rate. If the flow rate isn't up to the benchmark where it could keep up, it probably doesn't solve. So let's try 5,600 kilowatts. So the same thing, 5,600 kilowatts doesn't work. Let's say 5,000, 5,000 550 kilowatts. Still doesn't work. It's crazy. 5,010 kilowatts. 5,510 kilowatts. Still doesn't work. Let's see 5,000 and 5,000 and 5,505 kilowatts. Right, that works. But I'm pretty much sure there isn't much difference between 5,500 and 5,505 kilowatts. So it's not going to get us to the benchmark we need to be. So 5,509. Does it work? It doesn't work. So what this simply means is that the flow, the power right now, we're trying to bank on the power inputs to improve our hydrogen and oxygen production. Well, it's not going too well. So what we might need to do is to increase the flow so that we can add the power inputs capabilities. Basically, increase the power. We need to increase the flow so that it gives us a wider range of power inputs. And one of the ways to do that is that the best way to do that rather than just increasing it from the feed, because if we increase the feed, we're just shifting the goalpost. We're still going to reach that benchmark where we haven't attained a good yield and we have reached that mark for maximum power inputs for the with respect to the flow rate. So what we might need to do is we might need to recycle, because if you take a look at the amount of water present inside the oxygen, it's it's quite a lot. It's basically 81% of water. It's greater than the oxygen present inside the oxygen stream. For the hydrogen stream, it's predominantly hydrogen, which favors us, but we still have a little portion of the potassium hydroxide. And the purpose of this exercise is to produce hydrogen gas. If possible, it makes it better if we could produce a clean hydrogen gas without the potassium hydroxide. So what we might need to do is that we will need to recycle this water present here. We need to recycle this water present here to send it back to the system. With by doing that, we increase the flow, and this gives us a wider margin for power inputs. Now it sounds a bit confusing, but we're going to demonstrate that. So what we need to do right now is to separate our oxygen gas from the water and send back the water. And for the hydrogen side, we do not have much water, insignificant water. What we predominantly have is the potassium hydroxide. So we're going to hold on with sending back with recycling back the potassium hydroxide, because sometimes there's a maximum amount of flow that you could recycle. It could mess up the whole system. So we're going to keep it simple now. We're just going to send back the water. Before we do that, we need to separate the components into distinct components. We need to separate the mixture into distinct components. And the proper way to do that is to use a separator or column for better efficiency. But then to save time and energy, for this content, we're going to use a cheat black box, which we haven't used in our any of our contents. And that is called the component splitter. Yes, that's it. Component splitter. I'm going to drop two of that. Now, the component splitter, as I said, is a cheat black box, and the reason why I call it a cheat black box is because, well, my mentor does call it a cheat, definitely, and I agree with him. The reason why it's called a cheap black box is because it's an equipment which does not account for any process, yet it splits a mixture into distinct components without even doing anything and without showing you what process it uses. For example, a separator uses flashing to separate gas and liquids, and with that you have your distinct components in distinct phases. But here it doesn't do that. It just splits it. If you have hydrogen, if you send in water, which is H2O, it's just going to simply H2 split oxygen differently from hydrogen efficiently, 100% efficiently, which doesn't really make sense. And we're going to see what I mean by that. Firstly, we impute our inlets. Looking at the O negative. So let's start with the O negative, and energy stream is optional, so we do not need to include the energy stream at the bottoms. Let's call this tail. Let's call this tail. And for the overhead, we're going to call it oxygen gas O2. All right, so we have a message for the unknown splits. We have to specify the splits, and we're specifying the splits with respect to feed fractions, the molar fractions. And in water, if you could look, this is a column for the components, all the components we're working with: water, potassium hydroxide, oxygen, and hydrogen. That's what's present inside our feed stream. So what we're trying to do right now is to separate oxygen gas completely from the other components present. Like, of course, we do not have hydrogen gas inside the oxygen stream, but we do have oxygen, which we're trying to separate from potassium hydroxide, which is insignificant and predominantly have water. And it's the water we're interested in recycling. So what we're going to do for the oxygen stream, this is the new stream that is going out. We expect only oxygen to be present. So we're going to impute 100% oxygen. This is our oxygen 100%, which is 1 because we are using feed fraction, which is 100% 1. And then for every other thing present in that stream is going to be 0, 0, 0. All right. And as you can see on the other side, tail, which is the bottom, this is where we have everything is present other than the oxygen, because every single mole of oxygen or percentage of oxygen is present in the O2 stream. Now we need to specify the overhead pressure. That's the outlet pressure basically that comes out both overhead top and bottom. So we're just going to say this is, let's just maintain, let's not account for any pressure drop because this process is not realistic. So let's just say 6.5, 6.5. All right, and we also have to specify temperature, I guess. Let's just say 75. All right, and it solves it. As you can see, for the O2, we have 100% gas. And if we enter that stream, you can see the flow rate, which is 34.67, and the composition is 100% oxygen. Now, remember for the oxygen, what we had was, for the oxygen, when we calculated the oxygen that we were able to produce after the electrolysis, what we calculated the oxygen to be was 34.65. So that 34.65 oxygen was present inside the mixture where water was also there. So we just removed that 34.65 and pushed it to a separate stream where it stands alone. And the reason why we call this a cheat black box is because there is no heating, no cooling, no flashing, no process, and yet it just separates it. And ideally, in the real life operations, there isn't an equipment, or I don't know of an equipment that does that. It's just magical. So it's just there to hypothetically and not theoretically, hypothetically save time and energy in Aspen Hysys, and that's what we're trying to do. You can say it's lazy, it's wrong, but then it's to save time to make this content shorter. So on the tail end, what we have is 100% water, 94% water rather, and 6% potassium hydroxide. And that's what we're interested in for our recycling process. And you can see that the flow rate is 221. So that's where the water, that's what we have for the water, 100% water and potassium hydroxide. That's the only thing we have here. And for the oxygen, 100% oxygen here. So we're going to do the same thing for the hydrogen outlets to be able to separate our hydrogen. And we're going to call this H2 and call this tail 2. Inject our hydrogen inlet, specify our splits. So for this end, we're looking at hydrogen. I think we wrongly named that our H2O. Pardon me. It's supposed to be H2. H2. Good. So for the splits, H2 we're expected to have 100% hydrogen present. That's it, and the rest is 0. We don't need anything else inside. 0. And then you can see that everything is present in the tail 2 ends except for hydrogen, because we removed all the hydrogen, 100% hydrogen, to a separate stream. And we have to also specify the pressure, 6.5, but nothing changes. We're not accounting for any pressure loss because initially the whole process is not realistic, so we don't have to make it realistic for any pressure drop. So what we have here, 75 Celsius also. We just gained a little temperature. So with this, we have separated our hydrogen. As you can see, what we have for our hydrogen, 139.8, and that's the hydrogen, 100% hydrogen, and that's the 69.27 kilogram mole per hour that we had for hydrogen when we calculated inside the mixture. It's just that it's separated now from the mixture. And what we have down here is predominantly our potassium hydroxide. As you can see, 99.3% potassium hydroxide and very insignificant water. So what we said is that we're not going to be recycling the stream for the potassium hydroxide because we want to keep things simple to not mess up our process. What we're interested in recycling is our water, which is inside this tail, which is present inside tail. So I think we could just repeat this. Is that better? All right, much better. No, just rotate this. Yeah, much better. And we could use our new knowledge gain. Just move this DOM label. Not the equipment label. Size label. Fortunately, I don't think we have access to doing that here. We don't have access to do that here. Let's just manage. So this is the oxygen and hydrogen. So I need you to take note of the flow rates that we have currently before we recycle, because we have already separated our oxygen and hydrogen gas. So as such, it's these two streams of H2 and O2 streams are going to completely remain 100% hydrogen and oxygen even upon recycling. The only thing that is going to change is the flow rates, and that signifies how much it increases the amount, signifies the increment of our hydrogen gas and oxygen gas production. So currently what we have for the H2 molar flow rate is 69.34 kilogram mole per hour. And for our O2, what we have is 34.67. So also take notes of the tail because this is what we're interested in. We're not dealing with the tail too. So for the tail, what we have out here, what we're supposed to recycle, carries a flow rate of 221.5 kilogram mole per hour. So we haven't recycled in all our contents that we've been doing. This is the first time recycling. So to recycle, you do not just plug back the stream inside where you want to recycle. Ordinarily, for us to recycle, we need to send back this tail stream inside our mixer. With that, we create a continuous process instead of having losses where we're having water, unreacted water in the electrolysis. We send back that unreacted water to react more and produce more hydrogen and oxygen. Because currently, what we have is that we only use about 20% of our water to generate the hydrogen and oxygen that we have. So we still have unreacted, about 80% unreacted water, which we could use to produce more oxygen to reduce waste and improve our efficiency. So we're going to recycle. But you do not recycle by directly plugging it back to an equipment. You have to drop the recycle equipment, which is this, and it's a sign that we are very used to. It's very generic. So this is what it looks like. And we have an inlet and outlet. All we have to do is just plug our inlets, which is tail, and the outlet, we're going to call this recycle tail. And we click on OK, enter, and it gives us OK. Now, for scenarios where you get an error message in recycle, it simply means that you have too much flow to recycle. Well, I don't know if that's the right word to use, but that's an error that I encounter a lot of times. So you have to split your flows in most cases, reduce your flow basically. I think there's a limit to flow, there's a limit to what you can recycle. So in our case, we're on the safe side. It's not too bad, so we can safely recycle this. But before we recycle it, take note that the pressure is 6.5 bar, and all the streams here are 7.5 bar. If we were to plug this in, it's going to affect our process because we've already designed or simulated our process based on that 7, not 6 actually. 7, it's not 7.57, 7 bar, because we have a loss of 0.5 bar in the cooler. So we have to pump this to 7.5 bar, and then it loses its own 0.5 bar in the process, and then 7 bar goes into the system to keep it constant without changing any parameter. So not to make our operations unstable because of any change. So we're going to drop a pump. We're going to drop a pump for the tail also, recycle tail. We just turn this around. Now let's flip it. And all we have to do is plug cycle tail, call this E pump 3, and give this an outlet of pumped recycle, and just give it an increment of one bar, puts us on 7.5 bar. So with this, we are good to go. We're good to go. We could just plug this. We could plug this to our mixer, carry out our recycling. All right, good. All right, good. So I need you to take notes of our yields right now. Let's see what our yields look like. So as you can see, for the O2, it's still constant even after recycling. It did not change. The same 34.67 that we had earlier is what we still have. But the hydrogen is also the same thing. What we have is still the same 64.34. And the reason for that is that we only recycled the stream. We did not improve the production conditions and criteria for more gas, and that is nothing other than our power. The reason why we recycle this for us to have a wider range of power inputs, and that's exactly what we're going to do. Remember that before 6,000 kilowatts was not supported because we did not have enough flow, but now 6,000 is supported because we improved our flow. And this is where we're going to keep tweaking with the power to see how we can attain that good yield for our oxygen products yield for our oxygen and hydrogen. It's just like the scenario for those of you who have been following us down this far, the scenario where we were dealing with our distillation column, where we kept on tweaking with the overhead vapor rates to get the good product yield. So something similar to that here. It's going to be very stressful, but then I think we're going to skip those parts and just give you the good power, the good power inputs that gives you a very good yield. But let's just look at it now. Let's see, we're not even going to work with kilowatts because I'm pretty much sure that we have to jump to megawatts. So let's just say we have 10 or 1 megawatts, 10 megawatts. Let's just say we have 10 megawatts. We jumped from 5,500 or 6,000 rather, 10 megawatts, and you can see it's supported. So let's say we go to 15 megawatts. It's supported also. Let's go to 16 megawatts. It's supported. Let's go to 20 megawatts. And you can see it's not supported. But before we give up that it's not supported, remember the scenario in the overhead vapor rate in our column where we made our approach for increments gradual, because when we take a very large increment range, it messes up the column. Aspen Hysys sometimes is very dumb, or I want to believe that I am the dumb one. Maybe I haven't found out the secret to this. But then when we make our increment gradual from 1000, we understand that 1500, sorry, 15 kilowatts is supported. From this point, we make our increments gradual by about 2 kilowatts and by about 2 megawatts. Is it megawatts? Yeah, 2 megawatts to see if it works, because the range was too great for us. From 15, we moved to 20 megawatts and it messed up everything. So let's see, we're going to 17 megawatts. It Works. 19 megawatts. Roots. Let's see. 19.5 megawatts. Works. And 20 megawatts. As you can see, also works. But when we take that range in a very huge range, it just messes up the whole configuration for the equipment, and it just draws us back that we have to take that increment in ranges. So advisably, you take your increment in smaller ranges. So as you can see, I was able to take mine to 21.5 megawatts with very little increments of around, just increasing by 0.5, 0.5 from 20 megawatts. I went to 20.5 megawatts, and from 20.5 went to 21 and 21.5, and I'm currently on 21.5 megawatts. So with that, let's look at the composition. As you can see, we have 89. We have 89% for our hydrogen and the hydrogen, and we have about 9% for 9%. Yeah, we have about 9% for our potassium hydroxide, and about 2% for our water. For the oxygen, we have 13.8% in the oxygen stream, and water of 0.8348, and this is the inlet to the electrolyzer. But remember, this does not give us our yield, it's just the percentage composition in each of the streams. So, as you can currently see right now, we have our molar flow rates to have jumped from about, what were we having before? We were having about 34.67, and it has spiked up to 135.4. This is what signifies that we have produced more oxygen. And for the hydrogen, we spiked up from 69.34 up to 270.8 kilogram mole per hour. So this signifies our increment, and we're going to shortly look at the recovery rates to see where exactly we are. I think we are in a good position, because the total amount of hydrogen present in water was 277.7, and we currently have 270. So that's very good. And for the oxygen, I believe it was about 30. Was it 34? It was 138, and we currently have 135. So that's greater than 95%, I believe. But another very important and mind twisting thing that we all need to look at is the recycling, the output of the recycling, the output of the recycle process. Remember, for the recycle, what we had was 221.5 kilogram mole per hour. That's what we had. But after recycling, suddenly it just changed. It became 845.9. Became 845.9. So all of a sudden, it just changed after recycling. And the reason for that is the increments that we made inside the electrolyzer, the power increments. This generates more. It generates more flow, because we're generating more products, generates more flow, and ultimately affects this recycle process. And as you can see, initially before recycling, what we had before recycling was, let's take a look at that. What we had before recycling was, not for the pump, for those two streams. Okay, pumped H2 and pumped potassium hydroxide. What we had was 277.5. For the pumped potassium hydroxide, we had 26.74, and that gave us a total of about 304, if I'm right. I noted that down somewhere. That gave us a total of 300 and 300 and noted that somewhere. My notepad is also a bit messy, so pardon me. I'm trying to look for it. 300 and, oh, you know what? I believe I did not take note of that. It was around 300 and something. the sum of the two streams. After I adding the recycled stream, and remember initially the recycled stream was only about 220 something. So virtually we're supposed to be around 500 and something. But then instead we're around 1,000 and something. It doesn't add up. The mass doesn't add up. And the reason for that is just because of this recycling process and increment in power, which leads to increment in our flow. And it just changes everything that we can't easily account for it. So that's just the downside that I face when recycling. I don't know. Like I said, I want to believe that I'm the one who is a bit dumb and I haven't used the right logic to approach the recycling process, but it's something that I always face. So it's very important to always take note of your flows before you plug in the recycled stream. So to our yields, calculate our yields, we're going to be doing the usual recovery rate is equal to input, the input output, product output over product input. And the product output currently is 270 for hydrogen gas. Take note. The hydrogen gas is 270.8 all over 277.7 times 100. And that gives us 277.7 all over, oh, I got it the other way around. 270.8 over 277.7, 7.7 times 100 gives us 97.5% of hydrogen produced from our water distillation electrolysis basically. And for the oxygen, we have the input, the output of 135.4 over 130, 138.8 was it? Yes, times 100, so 135.4 all over 138.8 gives us 97.55% recovery also. So as you can see, we have successfully hit our required benchmark. Yay! It wasn't easy. So with this, we have successfully reached the end of today's content. It's very long. Hopefully you followed us down this far. As always, please make sure to like, subscribe, and click on the notification icon and leave a comment if you found this content helpful. As always, see you soon in our next content. It's going to be wild.